Hi class, how y'all doing today? Today's our first video for week 3, and what we're going to be talking about is addition and subtraction of integers and multiplication and division of integers. And so what we're doing is moving beyond our restriction of only talking about positive numbers, and we wonder what happens if now subtraction can go into the negative realm. And then once we talk about that today, our negative integers, we're going to move on to rational or fractional numbers starting tomorrow, and we're going to use those throughout the rest of the week as we step through the operations of addition, subtraction, multiplication, and division. And so this week, Thursday morning at 11, what we have due is Journal 2, Homework 5, and Homework 6. And so just make sure when you're answering your journal responses, you're attending to those 4 or 5 kind of big ideas it wants you to mention if you want to get full credit. And then Thursday from 11 to 11:50, we'll have our last quiz of the semester, because a week from then will be our final class and our final exam. And I'll give you more about that at the beginning of next week. And so just a reminder, Tuesday, we're not meeting 11 to 11:50. On June 2nd, we're going to be meeting 9 to 9:50. That's because I have a webinar that I can't miss. So that's what we'll be doing for this week. So like I said, what if we look back at our definition for subtraction? And remember, we said subtraction was defined as long as we had A and B with A bigger than B. That meant we would get a positive difference back. But what if we don't require that? What if we don't require that it's greater or equal to? Well, we get the negative numbers, right? And so the integers. This is not only our whole numbers, our 1, 2, 3, 4, 5, and on and on and on, but also our 0 with our naturals, and then going down into negative, and on and on and on. And so our integers is that set right there of all positive and negative whole numbers together with 0. And so we care about negative numbers because there are a lot of real life contexts in which they're important. Temperatures below 0, right? So in Celsius, below freezing is negative. Once we hit negative or 33 degrees below freezing, we get -1 in Fahrenheit. Buildings with basement stories, right? We're going to have basement 1, basement 2, basement 3, and so on. Locations below sea level. So if we're going to talk about altitude there. Amounts owed, right? You can owe someone money, which is in essence a negative amount of money that you have. And then in physics, negatively charged particles. And we mention that one here because we end up using what's called the charged particle or chip model for positive and negative integers in just a little bit. So looking back, this is from week 1. We talked about some sets of numbers. And so we know our counting and natural numbers. That's where we started. And so this week today we're going to be talking about integers. And then this next one, are rationals. All of those that can be written as some number over another will be starting tomorrow. So the set of integers is denoted with this double Z. And so you draw this with like a 7 and like an upside down 7. That's our integers. And then if you want to just talk about the positive integers, you can put a plus there. And it looks like that. Or if you just want the negative integers, right? And the positive integers is really the same as the naturals. But then I usually lump in 0 with the naturals. So 0 is neither positive nor negative, and so it won't fall into either of these. So if you want a list from 1 and higher, I would say go ahead and start using this Z positive to denote positive integers. And what's so special about these numbers? Well, they get paired up, and the negative integers are the opposites of the positive integers. And what that means, so -4 is the opposite of +4, 3 is the opposite of -3. And they're not just opposites because they get paired up this way, but it's because they're additive inverses. So that means if I take 4 and I add to it -4, I get 0 back. So that's our additive inverse property. And so that's why we call these opposites, because they in essence take away the same amount. If we also look at a number line, so 0, 4, -4, and we'll talk about this in a little bit, they're opposites because it turns out that they're both 4 units away from 0. And so we can think of it as that. They're on the opposite side of 0, but the same distance. So in the chip model, positive integers and negative integers are represented by 2 colors of chips. So for example, in Tuesday's activity, we're going to use blue for positive and red for negative. And so the rules for this are 1 red chip or 1 negative neutralizes 1 blue chip. They make what's called a 0 pair. So a red and a blue is 0, just like a positive 1 and a -1 is 0. So for example, this representation here is -1, because if we circle our 0 pairs, these together give me 0, and these give me 0, and I'm left with 1 red. And 1 red is a negative, and so this is -1. And so -1 could be represented with just 1 red chip, 2 red and a blue, or like here, 3 red and 2 blue, and so on, right? And so we can have any number of 0 pairs, because 0 isn't going to change the number, and not change the value. So here are lots in the top, lots of representations for 2, right? So we have 2 positives, or 1 0 pair, or 2 0 pairs, or 3 0 pairs, but in each case we're left over with 2. And the same with -2, we have 1 0 pair, 2 0 pairs, 3 0 pairs, but in each case we're left with 2 red, which is our negative. And so this is how we're going to model our positive and negative integers. But here's this image I was talking about. So -6, red is the opposite of 6, or as -6, is the same distance from the origin, or 0, as +6, and that's why we call them opposites. And then we have a special name for this distance. So the distance on the number line from 0 to any number is called its absolute value. So because, say, -4 is 4 units to the right, the absolute value of -4 is 4. But if we have the instance of, say, 5, the absolute value of that is just 5. So if you want to think about it, if it's negative, it becomes positive, and if it's positive, it stays the same. But in any case, it gives us the distance between the origin and our number. So adding. So if that's what our idea of integer or positive and negative integers are, there are these opposites, these additive inverses that we can model with red and blue chips. How do we model addition? Well, first we can use the number line. So when we're just adding 3 plus 5, we use this little cat animation here, but the cat starts at 0, walks 3 to the right, and then it has to walk 5 more to the right, and we end at 8. And so 3 plus 5 is 8. And then if we want to talk about a negative plus a positive, well, that's not so bad. We're just walking backwards 3 to -3. And we walk forward 5, and we end up at +2. And so we can start to see that positive means right, and negative means left, which you can see on the number line. But now what if we have -3 plus a -5? Well, we travel left some, then we have travel left some more, and we're left at -8. And now the last one. If we have 3 plus a -5, now we go right 3, left 5, and we end up at 2. But notice, in every case, we had a plus. So this is how we model addition. Of course, integer has properties. So you could use the chip model. You could do the combination of two sets, and the activity for Monday will do just that. But if we look at the combination of sets, or if we look at the integer number line model, what we see is that every time we add two integers, we'll get another. So we have closure. We have commutativity, so we can switch them in any order. 2 plus 3 is the same as 3 plus 2, or negative 2 plus 3 is 3 plus negative 2. Associativity, you can add them in any order, like in any clustering. You can put pairs with each other and it won't change the answer. We have an additive identity. This is the same as whole numbers. You can add 0 to something without changing it. But we now have the additive inverse, and I started to talk about additive inverses. So for every integer a, there exists a unique integer which we call negative a, or opposite of a, or the additive inverse of a, such that a plus its opposite is 0. And because of commutativity, we can do that addition in either order. So for 4, 4's opposite is negative 4, but if we say have negative 3, its opposite is just 3, because negative 3 plus 3 gives us 0. So subtraction. So addition, relatively straightforward, except we have this new rule about how we account for positives and negatives. We need two colors of chips when using our set model, or we just talk about direction. We give a specific orientation to our number line and we follow that. But for inner subtraction, it's a little bit more work, and so I'm going to go ahead and show you this example. 4 minus 7. Now we know that it's negative 3, right? We know that 4 minus 7 is negative 3. We'll first start with 4. And then I need to be able to take away 7. So minus a positive 7 means take away 7, and 7 positive, so we need to take away 7 blue. I only have 4, so I'm going to add 3 0 pairs. Put them in our frame, and then we get this one. And so now, because we have those 3 0 pairs, we didn't change it. The value is still 4, but let me go ahead and erase that. Because now, instead of circling my 0 pairs, I want to take away my 7 blues. So I have 2, 4, 5, 6, 7, take away all of those blues. And what am I left with? I'm left with 3 red. Red is negative. We're left with negative 3. So this is how you show through actually physically taking away why integer subtraction works. We have this notion of 0 pairs that cancel each other out. You can add 0 to a number without changing it. And so we just do that until we can take away enough of our positive chips. And then for the number line model, we're going to add a little bit of rules for subtraction. So we always start at 0 and face the positive or right direction. Okay, so we're always facing positive, the positive numbers. If the number is positive, we're going to walk forward, and if it's negative, we'll walk backwards. We won't turn around, we'll just literally step backwards. And then if you have a subtraction, whatever you do, the first thing you do is you turn around and face negative. And so let me illustrate this. So if we had 3 plus negative 5 equals negative 2, we get this, and so to model it with subtraction. So first we have 3, we start at 0, and we move right 3. Then we get to a negative sign, which means we turn around, and then negative 5 means we walk backwards 5. And we end up at 8. So 3 minus negative 5 is 8. Because you start at 0, you walk 3, you turn around, and walk backwards 5. And you end up at 8.